Welcome back to the DISA online tutorial. So we'll be looking at differential equation. We'll first start with solving first order differential equation. So we'll be looking at differential equations. So differential equation is any equation that has derivative in it. So when you have any equation, let's say y plus dy by dx equals 9 or something. So for us, we have our dy by dx here, which is a derivative. Then we can see that this equation is a differential equation. Now there are some terms used in differential equation that as students you have to take note of. So the first one, I'm looking at the order. So when you say the order of a differential equation, it refers to the highest degree of the derivative. So when you have a differential equation, let's say y plus d squared y over dx squared plus, let's say, 8 equals 0. So when you have something like this, then we can say that the highest derivative here is d squared y. That means it's a second order differential equation. Supposing you have multiples derivative, let's say y prime plus y prime prime plus y prime 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 equals 0, then we can say that the order of the differential equation will be order of 3, because the highest derivative here is y prime prime prime. Now let's take note of this. In differential equation, when you say y prime, then we mean dy with respect to an independent variable, let's say x, or dy with respect to another independent variable, let's say t. So this will be the conversion we're using here. So when anytime we see y prime prime, then we mean d squared y over dx squared. The second terminology you have to take note is dependent variable and independent variable. Then independent variable. Now when you have any equation, not only differential equation, but then any equation, let's say y equals a function of x, right? Our x here, because our x here can be varied, so we'll call our x independent variable. It doesn't depend on the value of y, but then y rather depends on x. So let's say we have our y equals 2x cubed plus 4x squared plus 8. The moment we change our value of x, let's say x equals 3, then we get a different output for y. When you change our value of x equals 2, we get a different output for y. Then we can see that our x here is our independent variable. It doesn't depend on any other variable in the equation. Then our y here becomes our dependent variable. So I think these equations are enough. These terminologies are enough to understand the basis for our differential equation. Let's begin with solutions for differential equation. Right, one more thing I was supposed to touch on was ordinary and then partial. So we have ordinary differential equation. So ordinary D is represented as OD. So anytime you see OD, it means ordinary differential equation. And then we have partial differential equation, also noted as PDE. So now with the ordinary differential equation, it's just like the name implies, our normal differential equation. When it is dy over dx, then we say this is an ordinary differential equation. For the partial, it's not fully. So the partial, it's in mathematical sense, when you have our function y, which depends on a lot of independent variables, let's say y equals x squared plus y squared. Y equals x squared plus z squared, right? Because y depends on two other independent variables, then we can see that when you want to differentiate y with respect to one of the variables, that's called a partial derivative. So something like this over ux, and then we can have partial derivative of y with respect to z. So the partial is like we want to differentiate the function here, but then when you differentiate with respect to one variable, that wouldn't be a complete differential. That's why you're calling it a partial one. So with this one, when we want to differentiate y, let's say we want y prime is supposed to be our y dx. So this becomes our partial derivative because it depends on x and then z plus, let's see, something like this. So now everything here becomes a complete differential, but then each of them becomes a partial derivative. So the partial derivative is noted as rho, something like this. Yes, so anytime you see something like this, then we are dealing with partial differential equations. But then the ordinary one, when you have d, so with the ordinary one, it's like the dependent variable depends on only one variable. So y equals 2x. We want to find the y by the x. That will be an ordinary differential equation. The y by the x, and that will give us, let's say, 2. So let's take note of that. So now the solutions of the differential equation, we'll be looking at ordinary differential equation. So we'll be solving ordinary differential equation. Now, there are a lot of methods used to solve ordinary differential equations. So the first one we'll be looking at, now, how do you know that a solution that you've gotten is actually the solution to the differential equation? Right. So our first one we're looking at solution. Now, when you say a solution, obviously it's your answer to a problem, right? So let's say we have a problem, a differential equation, 4x squared y prime prime plus 12xy prime plus 3y equals 0. And then someone is telling us that for this ordinary differential equation, the solution is actually y of x is equal to x exponent minus 3 over 2. How do we determine that indeed the solution the person is proposing is actually right? So we take our equations and then we substitute what we have into the equation and see if the left hand side will equal to the right hand side. Now all these are left hand side, right? And then this is our right hand side. Now our equation says that 4x squared y prime prime 12xy prime plus 3y. So just have to substitute this into the equation. Now you have y prime prime and y prime. So how do we substitute that? It means that our solution, you have to find y prime of that. And that's differentiating the dependent variable with respect to the independent, which is dy over dx. And that will give us minus 3 on 2x, negative 3 over 2 minus 1. And that will be minus 3 on 2x minus 5 on 2. Now the equation has y prime prime, so we evaluate y prime prime. We're going to differentiate this again, this minus, right? So we are differentiating minus 3 over 2x exponential negative 5 on 2. So that will give us minus 3 on 2 multiplying minus 5 on 2 x exponent negative 5 on 2 minus 1. And this will give us 15 on 4 x minus 7 on 2. Then we substitute all this. So we substitute this, and then y itself into the equation. Whenever we see y, we substitute this. Whenever you see y prime, we substitute this. Whenever you see y prime prime, we substitute this. So with the 4x squared plus, sorry, so now our 4x squared multiplied by y prime prime. So this is our y prime prime. 15 on 4 x exponent minus 7 on 2 plus 12x times y prime. So y prime is minus 3 on 2 x exponent negative 5 on 2 plus 3y. So this is our left hand side. So let's evaluate this. 4 divides 4, and then we have 15. We have x squared, we multiply by x to the power negative 7 on 2 So we add them because they have the same basis, right? So we have x exponential -3 on 2 plus 2 divided 12 6. So our 6 times our -18 here becomes -18. And then our x here multiplied by x exponent -5 on 2. So we add them, giving us -3 on 2 plus our y is x exponent -3 on 2. So 3x exponent -3 on 2. Then we add them. They all have x exponent -3 on 2. Sorry, so this x -3 on 2, -3 on 2. So we can add them. 15 plus 3 will give us 18 x exponent -3 on 2. And then we have -18 here. So this gives us 0. Then we can see that our left hand side is equal to our right hand side. Then we can conclude that indeed the solution to this differential equation is actually y of x is equal to x exponential -3 on 2. That becomes our solution. So now we are trying to find the solution to the differential equation. So we've been given our differential equation. We are still looking at another differential equation. We've been given a differential equation, then we want to propose a solution for that. Now there are a lot of methods that we can use to solve the differential equation, depending on the type of differential equation we have. There are a lot of methods. We can't cover all, but then there are some key ones we should know as students. So our first one we'll be looking at is separable. Right? So you can take note of that. So we have a separable, we have a linear, when the differential equation is linear form. We have when it's exact. We have when it's not exact. Right? So we'll take each one of them and then we'll go through. And then, so the last one is, you can see substitution. So there are a lot of different methods. I remember we have Riccati, we have Bernoulli. So there are a lot of them that I'm not sure we can cover all, but then we'll do the important ones that we need. So we're starting with the separable. So the separable is like when you have a differential equation and then it's separable. But then how do we know that the differential equation is separable? So we can only tell that a differential equation is actually separable when we can write the differential equation in the form m of x dx being equal to n of y dy. So what does this mean? It means that anytime you have a differential equation, but then we can separate it in the form that we can have a function of x alone. So let's take note of this. A function of x alone attached to the x and a function of y alone attached to the y. So the inverse is also true. So a function of x attached to the y equal to a function of y attached to the x. So one thing you should take notice, the functions here. So the function, when you have any function on the left or on the right, sometimes it could be that the functions have been added, right? Something like m of x dy plus n of y dx being equal to 0, or m of x dx plus n of y dy being equal to 0. So one thing we should look out for is our functions here. So we could see that our function should always be a function of x alone. There shouldn't be any y. And then our y here should always be a function of y alone. There shouldn't be any x. If there should be any x, then they should be multiplying. Right? So anytime you have something like a function of x multiplying a function of y, dy or dx, then we can say this is separable. Anytime they are dividing, right? So a function of x divided by a function of y, dy by dx, then we can see that they are separable. But then what if you have a function of x, y with a function of n also x, y? So when you have something like this, both m and n are functions, right? But then m contains a function of both x and y, something like 2x plus y. So this is for only m. And then n as another function of x and y, let's say x squared plus y. So when you have something like this, then it means we can't use the separable method, or we can say that the differential equation is not separable. it means that we can't separate the x from the y completely. But then when you have a function of m which consists of both x and y, but then the x and y are being multiplied, so something like 2xy all being dedicated to m, and then n also has x squared y. So anytime they are multiplying, then we can see that we can separate them. But then when they are adding, we can't separate them. So let's take note of that. So let's try some examples. So when you have a function y prime equals 3x squared plus 4x minus 4 all on 2y minus 4. So when you have this, is this differential equation separable or not? Now, let's use the choice I proposed. So now you have the numerator being only a function of x. So let's take note of that. So this is only a function of x, and this part is only a function of y. So, and then they are dividing. So since they are dividing, like I said, when they are dividing, you can see that this is a separable differential equation. So then we can solve them using the separable method. So we just group like terms. We group the x aside and then group the y also aside. Then you can multiply 3 by the denominator, and then we'll get 2y minus 4 y prime being equal to 3x squared plus 4x minus 4. Right? But then we know that y prime is equal to dy on dx. So yeah, our y here is a dependent variable and our x is an independent variable. So 2y minus 4 dy on dx equals 3x squared plus 4x minus 4. So we can separate them. So now they're separable. Let's go back and then see something here. Mx of dx equals ny of dy. Right? We'll separate them. You have our 2y minus 4 dy being equal to 3x squared plus 4x minus 4 dx. Right? So we've now separated our y from our x. Now we're going to find the solution to this differential equation. Since we have dy and then dx on both sides, then using the separable method, we are just going to integrate both sides. So we are going to integrate this function with respect to y, and then we'll integrate this function with respect to x. Right? So when you integrate 2y minus 4 with respect to y, they are going to have 2y squared on 2 minus 4y. Of course, integration, we have a constant, right? So we can put a constant here. Let's say k1 equals, when you integrate this part with respect to x, 3x cubed on 3 plus 4x squared on 2 minus 4x. We're going to have another constant, let's say k2, because probably the constant might be different. So 2 divides 2 here, we have y squared minus 4y plus k being equal to 3 divides 3 here, x cubed plus 2 divides 4, 2x squared minus 4x plus k2. This k1. Right? So I don't move on to the next page. Yeah. You can actually clean this part. Yeah. So we have y squared minus 4y plus k1 equals x cubed plus 2x squared minus 4x plus k2. So now this is what we have. Now, so let's group the keys. Now, the k1 and the k2 are constant. So then we can add them or we can subtract them to form another constant. So if there's a constant, let's say 3, this is a constant, let's say 4. We can still group them to form another constant. So what mostly we do is that we send the k1 to the x part and then we'll call it, so in our new differential equation becomes y squared minus 4y equals x cubed plus 2x squared minus 4x plus k2 minus k1. Now k2 minus k1 will still give you a constant as your answer, right? So if you're having 3 minus 1, 2, 2 is still a constant in this context. So we just call it y squared minus 4y equals x cubed plus 2x squared minus 4x plus k. Right? So in order to avoid all these steps, bringing the k1 to the k2 and then adding them or subtracting them to get a final k, what we do is that anytime you are integrating with respect to your y and then with respect to your x, we are not going to bring any constant for the y part. We just introduce a constant to the x part and call it k. That's all. I hope you understand this. So now our solution to the differential equation becomes y squared minus 4y equals x cubed plus 2x squared minus 4x plus k. Now this becomes our solution to the differential equation. Let's take note of something here. Right. So our differential equation is y squared minus 4y equals 3x cubed. So it equals x cubed plus 2x squared minus 4x plus k. So there's no 3 here. Now realize that when you want to find a solution to the differential equation, our solution should always be y equals something, a function of x. But in this case, we don't have y standing out explicitly, right? So we can try and make y the subject. Now in real life or in real differential equation problems, anytime they give you the problem, so our problem was this, right? They give you an initial value problem, or we call it our initial conditions. So anytime they give us a differential equation, we provided with an initial value conditions, right? Yes, or IVP. Right? So the IVP will help us determine what actually the case, so we can get our solution to the differential equation. When I provide this solution as the solution to the differential equation for this question, now someone might ask, so what is the value for k here? We don't know. So when k is 2, we get a different value. When k is 3, we get a different value. So what is our value for k? So they give us our initial value conditions or our initial conditions. The initial conditions, like given the differential equation or the problem, they can give an initial value problem to be y of 1 is equal to 3. So that means when you substitute 1 into this equation, you are supposed to get 3. I don't know if you get it. Y of 1 is equal to 3. Right? So now when you make y the subject from this equation, and then when you substitute 1, we are supposed to get 3 as our solution. And that will help us get our key here. Now, when you want to make y the subject from this equation, it will be very complicated. So what mostly I do is that I just substitute the initial conditions into the problem. Sorry, into the solution I have here and find the key before I try making y the subject. So we have y squared minus 4y being equal to x cubed plus 2x squared minus 4x plus k. We know y of 1 is 3, right? And our function is y of x. Our solution is y of x equals something. So if y of 1 is 3, then it means that when we put 1 into the equation, our value for y is supposed to be 3. Or when our independent variable, which is x here, is 1, our dependent variable becomes 3. So when you put 1 here, you are supposed to get 3. So wherever you see y, you are going to put 3 there. Wherever you see x, you are going to put 1. That's what it means. So we have 3 squared minus 4 times 3 equals 1 cubed plus 2 1 squared minus 4 times 1 plus k. So this gives us 9 minus 12 equals 1 plus 2 minus 4 plus k. So this is 3 minus 4, negative 1 plus k. equals negative 3. Then our k becomes negative 3 plus 1. And that's negative 2. So we now have our k. So now that we have our k, we just substitute our k back into our solution, this, and see that y squared minus 4y equals x cubed plus 2x squared minus 4x minus 2. So if you want to find the actual solution, so the actual solution is we just making y the subject. So we know how to make y the subject from a quadratic equation, because these are independent variable and then our x is a independent variable, right? So like ax squared plus bx plus c, we want to make x the subject. So y squared minus 4y, and then bring all these x cubed plus 2x squared minus 4x minus 2. All this becomes our constant. So minus x cubed plus 2x squared minus 4x minus 2 equals 0. So when you have this, making y the subject will be negative b, plus or minus root b squared minus 4ac all on 2a. Our negative b here becomes, our b here is 4, right? So that becomes negative 4. So negative 4 plus or minus b squared. So our b is negative 4, right? So 16 minus 4 times our a is 1, coefficient of x squared, y squared, sorry, 1. And then our c, the whole of this. So we'll just put everything there, right? So everything there is, our c here becomes negative this. You just put everything here all over 2 times our coefficient of y squared, which is 1. So making y the subject actually isn't the actual solution to the problem. You can leave your answer in this format, in this form, and then you still be correct. So you shouldn't even bother making y the subject when the equation is complicated. So let's try our next question. When you have y prime being equal to xy cubed all on root of 1 plus x squared, and our initial value problem is y of 0 equals negative 1. So now let's see whether we can solve this problem with separable method. We have x here and then y cube here, but then they are multiplying, they are not adding. And then in this part, you have only a function of x, even though it's being added, but then here is 1. Supposing here was y, then we can't solve this with the separable method. So y prime equals xy cube all over root of 1 plus x squared. So let's try separating them. Bring our 1 plus x squared here. So y prime root of 1 plus x squared equals x y prime. Now we want to group the x to one side and then the y to the other side. So what you can do is that you can actually divide through by x here, or then you can divide through by y cube. The division will depend on our y prime here. So our y prime here is actually dy on dx. So let's substitute that. So dy on dx 1 plus x squared equals xy cubed. Now we always make sure that our dx is being attached to the function of x, and then our dy is being attached to the function of y. We bring our dx here. That means our function of x should be on the right, and the function of y should be on the left. So it's advisable to divide through by y cubed instead. Cancels out, and then we get 1 over y cubed dy on dx. Everything multiplying 1 plus x squared equals x. Then we can again divide through by 1 plus x squared. Sorry, root of 1 plus x squared. Then this one goes. We are left with 1 over y cubed dy being equal to x over root of 1 plus x squared dx. Now we separated our y from our x. Then we can integrate both sides. When we are integrating 1 over y cubed with respect to y, so y exponent negative 3 dy. And then this part, we are integrating x over root of 1 plus x squared dx. So now in the separable, we are really going to make use of our integral, our integration and stuff. So when integration is not really strong, you will suffer with differential equation because mostly you'll be integrating stuff. You want to integrate y squared minus 3. You know how to integrate such problems. You add 1 here, you divide through by the power equals. I said we shouldn't wire ourselves bringing a constant here. And then when we want to integrate this part, now this isn't as simple as it is, right? So we're going to integrate this part using the substitution method, right? So we've done calculus 1. So we can see that let u be equal to 1 plus x squared, right? So our u is 1 plus x squared. And then we say that du over dx, when I want to integrate, when I want to differentiate the u with respect to the x, I get 2x. And then I'll make dx the subject. So my dx becomes du on 2x. And I put it here. Right? So to integrate using the substitution, you should always have a foresight that the functions of the x over the functions of the y, when I differentiate, will I get a multiple of the one on top or the one on down? If yes, then you can go ahead using a substitution. So when you have something like this, 1 plus x squared, so you can glance through. When I differentiate 1 plus x squared with respect to x, what do I get? 2x. Is it a factor or a multiple of the numerator x here? Yes. Actually, 2x is just 2 times our x here. So if yes, then I can use a substitution. That's why I went ahead to say let u equals 1 plus x squared. Then I will put the x equals du over 2x back here. So let me clean this part so that it becomes visible for us to see. Right. So y exponent negative 2 for this part, right, all on negative 2 should be equal to, integrating this, integral x over, now we said let our u be 1 plus x squared, right? So that is going to be root of u. Now the x here is du on 2x. So du on 2x. X divides x. Then I left it. Negative 1 on 2y squared equals integral 1 over 2 root u du. We can bring our 2 out and see 1 over 2 integral 1 over root u du. Right. So now this becomes easy. Now I want to integrate 1 over root u. Right. So negative 1 over 2y squared should be equal to half. 1 over root u becomes u exponent negative half. Then when we want to integrate, we add 1 over negative half plus 1. And then I said that our right hand side should always take our constant, right? So plus our k here. Let me clean this portion. And please, I hope you are all following it and you understand it. If you don't understand it, you can put it in the comment section so that I go over again. Right. So negative 1 over 2y squared equals 1 over 2. Now u exponent negative half plus 1 will give us u exponent half. Negative half plus 1 will give us half. So 1 over 2. So here becomes 2 plus k. Right? So negative 1 over 2y squared equals half times 2. U exponent half is root of u plus k. So 2 divides 2. Right? Now we said that our u is actually 1 plus x squared. So we now put our u back. right? So negative 1 over 2y squared equals root of 1 plus x squared plus k. So negative 1 over 2y squared is equal to root of 1 plus x squared plus k. And then the question says that our initial condition was y of 0 equals negative 1. So wherever we see x, we are going to put 0. Wherever you see y, we are going to put negative 1 there. So negative 1 over 2. Negative 1 squared gives us 1. So this one becomes half, negative half. Root of 1 plus x squared, and x is 0. So 1 plus 0 squared plus k. So negative half equals, this will still give us 1 plus k. And then our k becomes negative half minus 1. Now it's minus 3 on 2. So now that we have k, we'll just put our k back into our original solution. So put our k back to our solution. And then we'll have negative 1 over 2y squared is equal to root 1 plus x squared minus 3 on 2, because our k here is minus 3 on 2. So we can leave this as our solution. But then if you want to make y the subject, you can go ahead and make y the subject. So you just find the reciprocal of that. But then if you don't want any issues, leaving the answer in this form is also correct. Or you can go ahead and make y the subject. We've done enough of the step problem. So let's move on to the next method. So our next method is linear, or in some we should call it integrating factor approach. Now, when the differential equation is in the linear form, so when do we see that the differential equation is in the linear form? We say that the differential equation is in the linear form when it can be presented in the form y prime plus p of xy divided equals g of x. So now let's define our terms here. Our y prime we know to be the 1 over the x. Our p of x is a function of x. So then when you have a differential equation which is in this format, so our y prime is on our left, our p of x, which is a function of x, being multiplied by y. So we should take note of this function of x here. The function of x is strictly a function of x. There shouldn't be any y in this function, right? Being attached to our y equals our right hand side is supposed to be g of x alone. So there shouldn't be any y here. It can be a constant, but it shouldn't be y. So when I have a function like y prime plus 2xy equals 2x plus y, I have my y prime here, 2x being attached to y, right? So our p of x. But then our g of x is 2x plus y. Because there's a y here, then this wouldn't be a linear differential equation. Sometimes a differential equation wouldn't be in this format as easy, but it can give us something like p of x y prime plus 1, or let's say plus y equals 3. Now we have to make it linear. It's not like you are going to enforce it, but then you are just going to make sure that our y prime stands alone. Because for it to be linear, our y prime should stand alone. So we divide 2 by p of x, everything by p of x, and see if it will be linear. So we have y prime plus 1 over p of x y equals 3 over p of x. So now we can see that this is actually a linear form, because if we have our y prime You have a function of x multiplied by y, and then we have 3 over a function of x here. So that means it is in the linear form. So when the function is linear, then the solution becomes, we define our integrating factor. So that's why some books they call it integrating factor. We define our factor called integrating factor. So u of our independent variable, let's say x. This integrating factor is equal to e, or exponential integral p of x dx. So let's take note of this. Right? Yes. So when we have the differential equation in the linear form, right? Now that we've reduced it into the linear form, something like this, we define an integrating factor such that the integrating factor is exponential integral p of x dx. P of x dx, and then we integrate this. Now after integrating this, our answer becomes u of x. U of x. So this becomes our integrating factor. This isn't our solution. And then our solution y of x becomes integral u of x, our integrating factor, multiplied by our function here, the one on the right hand side, which is merely a function of x or a constant. There should be any y inside. Multiplied by g of x dx. So I'm going to integrate everything this with respect to x all over u of x plus a constant k also on u of x. So this becomes our solution. You have to keep this formula in your head and also this. So our u of x is this. So you first have to find for our integrating factor, and then we should know our g of x, and then everything will be fine. So let's try some few examples. So example 1, dv over dt equals 4 minus 12v. Now we have this, and then so let's take, is it linear? Now we say that for a differential equation to be the linear form, it's supposed to be y prime plus p of x y equals g of x. Now what we have here is v, so we can say the same thing, v prime plus p of t, because now our t's are independent variable. P of t v is equal to g of v. We know that the v over the t is actually v prime. We can bring our 12v here. 12v equals 4. We have v prime alone. 12 So you can see that this is in the linear form. Right? So now we have to define our integrating factor, u of t, because our independent variable is now t. So u of t is actually equal to exponential integral p of x. Now this is our p, so it is 12 to 12 dx. Now when you integrate this, you get exponential 12x. So now this is our integrating factor. So our u of t is actually exponential 12x. Then we will substitute that into our formula for the solution to the differential equation when it is linear. We see that our y of t, our v of t is equal to integral u of x. So now it's u of t exponential 12x multiplied by our g of x becomes 4. So like I said, the right hand side is supposed to be either a constant or a function of x. So now this is a constant. So multiply by 4 dx all over u of x. So our u of x exponential 12x plus k over exponential 12x. Right. So our v of t becomes, now I want to integrate this with respect to x. We can bring our 4 out. 4 exponential 12x dx all over e 12x plus k over exponential 12x. When you want to integrate e exponent 12x now, when you have integral of e exponent mx, that will give us, you will differentiate what's here and then divide by that. So exponential mx all over m. When I differentiate mx, I get m. So the same thing. So our v of t becomes 4 multiplied by, divide through by 12, because when I differentiate 12x, I get 12 multiplied by exponential 12x all over exponential 12x plus k exponential negative 12x. So I just applied indices here. This cancels this. 4 divides 12, 3. So our v of t becomes 1 over 3 plus k exponential negative 12x. So this becomes our solution. We weren't given any initial conditions, so this will be our solution. Go to the next. So let's solve the last example on the linear. You have to the next example. We have cos x y prime plus sin x y being equal to 2 cos cube x. This. So now I have our differential equation in this format. So first of all, when you have the differential equation, you have to know whether you are supposed to use separable, integral, or this or this or this. The question wouldn't tell you. So from what you've done so far, you've done separable and then linear. So you ask yourself, can it be solved by separable? No, because you have a function of x here. It's being added to a function of x multiplied by y. They are adding. And then this one. Obviously, you can't use separable to solve this problem. So, and then for the linear, we said that we should have y prime standing alone. So our first step is to make y prime stand alone. So we divide through by cos x. Divide through by cos x. Cos x. Right. So cos x divides cos x. We have y prime plus sin x over cos x is actually tan x. So tan xy equals cos x, we cancel one of these. So we have 2 cos squared x. So now we have y prime, a function of x multiplied by y equals, and this is a function of x purely. So you can see that this is actually in a linear form. So you can use the integral method or the integrating factor approach. We define our integrating factor u of x is equal to exponential integral tan x dx. So the coefficient of y here. Now how do we integrate tan x? So we know tan x is equal to sine x over cos x. So you ask yourself, when I differentiate cos x, do I get a factor of sine x? Yes. So I'll say let u equals cos x. Du over dx is equal to negative sine x. I make dx the subject, right? My dx becomes negative 1 over sine x du. Then I put it here. So integral of tan x dx becomes integral of sine x over cos x. When I say let cos x be u, so over u dx. Now my dx is this, 2 times negative 1 over sine x du. I'm integrating with respect to u, so definitely this and this should cancel out. So then I have integral of negative 1 over u du. So when I want to integrate 1 over u, it's going to be negative ln u. So this is negative, so negative, and then this is a linear function, u alone, right? So ln u, and I put it back here. So my u of x becomes exponential integral negative ln u. But then I said let u be equal to cos, u of x becomes exponential negative ln u. I said u equals cos x, so we substitute it. So my u of x becomes exponential negative ln cos x. And then we know how ln works, right? So when I have negative ln cos x, it's actually equal to e ln cos of negative 1, right? And then we know cos of negative 1 is 1 over cos, giving us sec x. So ln sec x. When it's exponential, we know exponential is actually the anti of ln, natural log. So when they are together, it's just the function itself. Then I have exponential ln f of x. The answer I get will be just f of x. So exponential ln 5 will just give you 5. Right? So this will end up, so our u of x will just end up giving us sec x. So this is our u of x. So now that you have our u of x, we know that our y of x is equal to integral u of x multiplied by g of x all over u of x plus a constant k over u of x. We know our u of x to be sec x. Now what's our g of x? Our g of x is actually what's on the right hand side. So 2 cos squared x. 2 cos squared x. Then we put it into the general formula. So u of x is equal to integral sec x multiplied by 2 cos squared x all over sec x plus k over u of x is sec x. We know sec x is 1 over cos. So u of x is equal to integral 1 on cos multiplied by 2 cos squared x. So we are integrating with respect to x. Cos cancels one of these all over sec x plus 1 over sec x will give us cos. Because 1 over cos is sec x. So 1 over sec x will still give us cos. So k cos x. So our y of x is equal to, we can bring our 2 out. 1 over sec x will give us cos x. So this is cos x. For this part, integral cos x dx plus k cos x. When we integrate cos x, what do we get? We get sine x. Now y of x is equal to 2 cos x sine x plus k cos x. We know 2 cos x sine x is actually sine 2x. You can just see that our y of x is equal to sine 2x plus k cos x. So this becomes our solution to a differential equation. So you could either end here or you can go ahead and then end here. Now this becomes our solution to the differential equation. Because we weren't given any boundary condition. So we weren't given any boundary condition. So we'll just end here. So this becomes our solution to the differential equation. So our next method is the exact method. So with the exact method, when you have the differential equation m of x y dx plus n of x y dy being equal to 0, we can see that the differential equation is exact when dm over dy is equal to dn over dx. So when I differentiate m with respect to y and it's equal to the differential of n with respect to x, then I can see that the differential equation is exact. In such case, the solution becomes, I'll just integrate m with respect to x and then combine it with integral of n with respect to y, and that should be equal to my constant k. So this is it. So when you check for the differential equation, then it is exact. This is what you are going to apply. So let's try some few examples. So we have the differential equation 2xy minus 9x squared plus 2y plus x squared plus 1 dy on dx equals 0. When I have this, I have to make sure that the equation mimic what's here. So I can just multiply 2 by dx and get 2x minus y. Sorry. 2xy minus 9x squared dx plus 2y plus x squared plus 1 dy is equal to 0. So this is my m and this is my n. When I differentiate this m, everything here is my m. So everything here is my n. When I differentiate the m with respect to y, so let me differentiate this whole thing with respect to y. So dm dy is equal to 2x, and then dn dx is equal to 2x. Because they are the same, then I can see that this differential equation is exact. Then I can use the exact approach to this. My m is actually 2xy minus 9x squared, and my n is 2y plus x squared plus 1. So the solution, I'm going to integrate my m with respect to x and combine it with integral of n with respect to y, and that will give me k. So I will look at the combination. So integrating 2xy minus 9x squared dx will actually give me 2x squared y over 2 minus 9x cubed over 3, and that will give me x squared y minus 3x cubed. Now for the n parts, n dy equals integral of 2y plus x squared plus 1 dy. So this, you are going to integrate each part with respect to y. So 2y squared over 2 plus x squared y plus y. So this gives me y squared plus x squared y plus y. So with the combination, I say that we are going to integrate m with respect to x. You combine it with integrating n with respect to y, and that equals 0. So the combination, this is how it's now. I have x squared y here. You check for the end part. Do you have x squared y? Yes, so I'll just pick one of them. I have negative 3x cubed. I don't have any x cubed here, so minus 3x cubed. And this part, y squared, there is no y squared here, so plus y squared. X squared y, there is 1 here, so I've fit 1 already. I'll just leave it. Plus y, there is no y here, so plus y. And this equals key. So this becomes the solution to the differential equation. So you can go ahead and still make y the subject if you want, but then that will be a bit complicated. So we can just leave our answer in this format. X squared y minus 3x cubed plus y squared plus y equals k. We aren't given any initial condition, so we'll just leave our answer in this form. Let's say we're given an initial condition of y of 0 equals negative 3. So when x is 0, we're going to put y will give us negative 3. So x is 0, so this part will even go to 0. X is 0, this part will also go to 0. Y is 3, so this part will give us 9. And then y is negative 3, so minus 3 equals k. So our k becomes 6. And then we will write the whole equation and then put 6 here. Let's try one last method. Wait, one last example. So 3y cubed x 3xy minus 1 plus 2y cubed, sorry, 2y exponential 3xy plus 3x y squared exponential 3xy or y prime equals 0. And our initial condition is y of 0 is 1. We know y prime is dy by dx, so we can just put our dy over dx here. And then you can multiply 2 by dx. So we now have 3y cubed exponential 3xy minus 1 everything dx plus 2y exponential 3xy plus 3xy squared exponential 3xy dy equals 0. So these are m, this one n. Evaluating m with respect to y, which is differentiating m with respect to y, will give us, so this actually, we have y here and we have another y here. We are going to use product rule. So this will give us 9y squared exponential 3xy plus, now we differentiate what's here. So 9y cubed exponential 3xy. Sorry, so x should also come here. Yeah. And then when you differentiate n with respect to x, which is dn over dx, that will give us 6y exponential 3xy plus, so you are going to differentiate this part with respect to x also. You have x here, you have x here, so you are going to apply the product rule. So this will give us 3y squared exponential 3xy plus, this will give us So this part will also give us 9xy. So because when you differentiate 3xy with respect to y, you're going to get 3x, and that multiplies everything here. You're going to get 9x squared. Let me take it step by step. Now we want to differentiate m with respect to y. This is our m. In differentiating this with respect to y, we will differentiate this portion, multiply it with this, and then we add it to, we keep this one constant, and then we differentiate what's here. Now differentiating 3y cubed, we get 9y squared. And then we multiply that with what's actually here. So exponential 3xy plus, now we'll keep our 3y cubed and then multiply it with differential of this portion. This is a constant. So when I differentiate it with respect to y, that part will go to 0. So exponential 3xy. And I want to differentiate this. I will differentiate what's here. 3xy, when I differentiate, I get 3x exponential 3xy. My final answer becomes 9y squared exponential 3xy plus 9x y cubed exponential 3xy. And then with the end part, I want to differentiate this with respect to x. There is no x here, I just have x here. So this will be quite easy. I differentiate what's here and I multiply with that. So I get 6 so 2y multiplied by 3y. I'm differentiating with respect to x. Exponential 3xy plus, so this has x here, this one has x here. I'm going to differentiate using the product rule. So differentiating this part alone, I get 3y squared exponential 3xy. So I multiply it with that plus, now I keep this one constant, 3xy squared multiplied by, when I differentiate what's here, I get 3y exponential 3xy. So this will give me 6y squared exponential 3xy plus 3y squared exponential 3xy plus 9xy cubed exponential 3xy. So this will give me, they are like terms, right? So 9y squared exponential 3xy plus 9xy cubed exponential 3xy. So let's compare that with the n. We have 9y squared exponential 3xy, the same as this, and then this is also the same as this. Then you can see that this differential equation is exact. Then we can solve using the exact approach. We take note of our m. So our m is 3y cubed exponential 3xy. Then our n is 2y exponential 3xy plus 3xy squared exponential 3xy. So the solution is we integrate m with respect to x, we combine it with integrate n with respect to y, and that will give you k, and this is my solution. So when integrating 3y cubed exponential 3xy with respect to x will give me, so I'm going to integrate each term, right? When I'm going to integrate this with respect to x, I assume my function of y's are constant, right? So my 3y cubed is just a constant multiplying the exponential 3xy. I differentiate what is here and I divide by that. So 3y cubed exponential 3xy. And I differentiate what is here with respect to x. I get 3y. So this becomes my integral. 3y cancels 3y. So I get y squared exponential 3xy. Then when I want to integrate 2y exponential 3xy plus 3xy squared exponential 3xy with respect to y. Now this becomes, I want to integrate this with respect to y. So I can have, I'm integrating 2y exponential 3xy with respect to y. And then I'm also integrating plus 3xy squared exponential 3xy also with respect to y. Now come, when I take this part, because they are multiplying, supposing they were adding, I would have integrated both sides separately and then added them. But then they are multiplying. So what do I do? So that's when I can use the product rule in integration. So I say let my u be equal to y something. But then I have to check this. When I differentiate 3xy, do I get a factor of this? If yes, then I say then I can use the substitution approach. If not, then I have to use how do you call it? You have to use the product rule in the integration. So that one, you can see that when you want to differentiate, when I have f of g, or if I have u v prime, this is actually equal to u prime v plus u v prime. So I integrate both sides. And this one gives me u v is equal to integral u prime v plus integral u v prime. So I can see integral of any of them. So u v prime will be equal to u v minus integral u prime v. So now when I want to integrate a function like this, it's actually equal to u v minus integral u prime v. So I have to define my terms. I define what u is, I define what v prime is, and after I'll evaluate u prime, because when you want to integrate something like that, you need your u prime, right? And then you need your v, not v prime, but then we define v prime, so we find v of that. So this means what you take as your u, you differentiate. What you take as your v prime, you are going to integrate that to get your v. So that's the approach I'm going to use, because we can see that when we differentiate, let's say y here, when I differentiate y, I get 1. This is a factor of this, that means I can't use the substitution approach to solve the integral of this. Right? So this is the approach I'm going to use to solve that. So we have integral of 2y exponential 3xy 3xy dy plus integral 3xy squared exponential 3xy dy. Now for this part, you can see that when you differentiate y squared, because you're integrating with respect to y, see that when you differentiate y squared, you're actually going to get a function of x y here, right? So then we can see that we can apply substitution here, and then that one will also work. Or if not, we'll just use the reduction approach using this approach. So when we do that with this portion, integral of 2y exponential 3xy, we are going to get for this part alone. So you can try that. You define your terms. So define the terms. I think you should just try for the first one and then you do for the second one. So we are seeing integral of u v prime is equal to u v minus integral u prime v. So we define our terms. Which one becomes our u and which one becomes our v? Our v prime. We can select our u. So mostly the u is what you are going to differentiate, right? And then the v prime is what you are actually going to integrate to get our v. So we always want to make sure that what we are going to differentiate will be something we can differentiate till we get to 0, right? So it's something like this. So with something like this, I know that with the y, if I differentiate multiple times, I can get to 0. But then the exponential, irrespective of the number of times I integrate, I wouldn't get to 0, right? So I'll just choose my u to be y. I can bring the 2 out here, and then the 2 leaves. So y. And then my v prime becomes exponential 3xy. So now integral of this. So this is how you define it. Integral of u v prime. So this is my y. My v prime is exponential 3xy. Will be equal to uv. So now I have to find v. This is v prime. So I have to integrate this. When I'm integrating v prime, I get exponential 3xy all over. I differentiate what is here and I divide by that. Right? But then I'm differentiating with respect to y, not x. So I get over 3x. So this becomes my v. And then my u prime becomes 1. I just substitute that. U v. So y exponential 3xy all over 3x minus integral of u prime v. So where's my u prime? My u prime is 1. So 1 multiplied by v. So my v is exponential 3xy all over 3x dy. So we have this part. So y over 3x exponential 3xy minus, so I'm going to integrate this with respect to y. So now we see that our this one has left, our y here has left. So we are going to integrate this exponential 3xy over 3x with respect to y. Now that we are integrating this with respect to y, we assume our x's to be constant, right? So our 3x is nothing but just a constant. We've gotten this part, so we'll just write the same thing, y over 3x exponential 3xy minus. Now when I want to integrate this with respect to y, I differentiate what is here and I divide by that. So exponential, I have my 1 over 3x here, exponential 3xy all over, and then I differentiate what is here with respect to, I get 3x, I divide again. So then my answer becomes y over 3x exponential 3xy minus exponential 3xy all over 9x squared, because 3x and 3x. But then we brought our 2 out and then we integrated this. So the final answer should be 2 multiplying the whole of this. So you multiply everything by 2. And then we get our final answer to be 2y on 3x exponential 3xy minus 2 exponential 3x on 9x squared exponential 3xy. So this becomes the integral for only this part. Then we'll try again for this part also. We can go ahead and try for that one. So this tells us that in differential equation, you have to be very expert in your integration, otherwise you struggle a lot. So we have this for this part. So let's keep it safe somewhere here. So we have 2y on 3x exponential 3xy minus 2 over 9 exponential 2 over 9x squared exponential 3xy. Exponential 3x comes again. So let's evaluate this one. So 2 exponential 3xy. I repeated this one twice. So this one is not there. So exponential 3xy. So this becomes our integral for only the first part. Now our second part is this. We've already done we are left with this part, right? The end part. We've already done our end part, and that's what we had this. So we are left with our end part. That's what we are doing. So we are going to integrate this also with respect to y. I can say our n was quite complicated. So, okay, this was our n. So we are left with integration of 3xy squared. 3xy squared exponential 3xy with respect to y. So we can apply the same thing. Integral u v prime is equal to uv minus integral u prime v. U prime v. We can see what will be our u and what will be our v prime. Because we are using this to integral of something, right? So our u should always be the function that we can actually differentiate till we get to 0. Right? This 3x here becomes a constant because we are differentiating, we are integrating with respect to y. So our 3x here becomes a constant. You can actually see that this is equal to 3x integral y squared exponential 3xy. Yes, so we can have it something like this. So our u becomes something we can actually differentiate till we get to 0. You can differentiate the y till we get to 0. So I differentiate y squared, I get 2y. I differentiate again, I get 2. Differentiate again, I get 0. And then with the exponential 3xy, irrespective of the number of times I differentiate, I wouldn't get to 0. So we can even draw a table like this. Because when you want to use this thing, they are going to solve for long. With the first one, it was just y. So with the first time we differentiated, we had 1. Then everything was fine. And this, you have to differentiate 2 times. Because when you differentiate for the first time, you get 2y present. And differentiate again, you get 2. So we can just draw, and then we have our sign here, our differential, then our integral. So our sign is plus, minus, plus. We'll just alternate them. Minus, plus. So what do we want to differentiate? We are going to differentiate y squared. And what do we want to integrate? We want to integrate exponential 3xy. So when you differentiate the first one, what do we get? When I differentiate this, what do I get? I get 2y. I differentiate again, what do I get? I get 2. And then the next time, I get 0. With this, now I want to integrate. I have to differentiate what is here, actually. So 1 over 3x exponential 3xy. Then I will integrate this one again. But note, we are doing with respect to y. So my 3x is still a constant. So that one becomes 1 over 9x squared exponential 3xy. Then I integrate again. 1 over 27x cubed exponential 3xy. And I do this. So this is actually a shortcut in solving the integration when you have to use the reduction approach. So I get y squared multiplied by this. So positive y squared, because the sign here is positive. Y squared multiplied by 1 on 3x exponential 3xy. And the next sign is negative, 2 minus 2y multiplied by this 1 over 9x squared exponential 3xy. And then the next one is positive, so plus 2 multiplied by this. I didn't bother going ahead to integrate this because the next one will be 0 times that, which will give us 0. That's why it's advisable to take a function that you can actually differentiate to get 0. Then my next step becomes plus 2 multiplying 1 over 27 x cubed. Sorry, the x cubed is a denominator. X cubed exponential 3xy. So when you evaluate that, we'll be getting y squared over 3x exponential 3xy minus 2y over 9x squared exponential 3xy plus 2 over 27 x cubed exponential 3xy. So the whole of this right, is the integral for this part. So it looks complicated, and then the whole of this is also the integral for this part. So we just add them. We add it to this, and that becomes our complete integral for the end part. So 2y over 3x exponential 3xy minus 2 over 9 x squared exponential 3xy. Now we want to merge this with our n. Right. So we said integral m dx, we are merging it with our ny. So like how we did the previous one, integral of m dx is just y squared exponential 3xy. So we compare it with our n. So let's take y squared exponential 3xy, y squared exponential 3xy. This was for our m, and the whole of this was for our n. So we merge them. Y squared exponential 3xy. It doesn't appear in any of this here. So that means our solution becomes this plus this plus this plus this. But then we can add some like terms here. Oh, this 2 exponential 3xy, 2 over 9x squared, 2y over 3x exponential 3xy. So we can't add any of them. Okay, we have negative 2y exponential 9x squared. Sorry, I think we factorized something out here. We brought something out. This. So what we did was the integral for only this part. Right. So that means I have to multiply the equation we had, the whole of this, by 3x. So it looks complicated. So that's how differential equation becomes. Sometimes it looks very complicated, and then you have to still try your way to find a way out. You have to multiply the whole of this by 3x before you can get our actual integral. You can pick the question and then try again. You can try on your own. So where is it? Integral of 3xy squared exponential 3xy. dy. We want to integrate this with respect to y. So we can actually bring our 3x out. So then we are left with y squared exponential 3xy. So we'll choose our sign here, differential, and then our integral. I said plus, minus, plus, minus, plus. So what do we want to differentiate? We take a function that we can actually differentiate to 0. To y squared, 2y, 2, 0. A function that we want to integrate, exponential 3xy. When you integrate, you get 1 over 3x exponential 3xy. The next one becomes 1 over 9x squared exponential 3xy. The next one becomes 1 over 27x cubed exponential 3xy. This takes this, this takes this, this takes this. This one looks very simple. We get y squared on 3x exponential 3xy minus 2y over 9x squared. So this multiplies this exponential 3xy plus 2 multiplying this. So 2 over 27 x cubed exponential 3xy. Now this is for the integral of this part alone. And then we have to multiply 3x by all this. So 3x multiplied by y squared over 3x exponential 3xy minus 2y on 9x squared exponential 3xy plus 2 over 27 x cubed exponential 3xy. So 3x multiplies 3x here. So this cancels this. I left it y squared exponential 3xy minus 3x cancels 3 cancels 3. I left it 3 cancels 1x. I left it 2y over 3x exponential 3xy plus 3x cancels 27 9x squared to 2 over 9x squared exponential 3xy. So this finally becomes our integral for this part. The whole of this is the integral. So it looks like the integral for n was quite complex. It had two parts. This part and then this part also. It had two parts. This part and then this part. Yes. So we've now gotten the integral for this part. And then with this part, we had our answer to be this. We have to make them. N was completed. So 9 ny with respect to y. Our n with respect to y actually give us a complex equation. Y squared exponential 3xy minus 2y over 3x exponential 3xy plus 2 over 9x squared exponential 3xy plus the other part. So this was our n. It had this part and then this part. So this part was what gave us this. So this part gave us this 2y on 3x 2y on 3x exponential 3xy minus 2 on 9x squared exponential 3xy. So that was for this part. Yes. So this alone was for x. For this alone was for n. We have negative 2 9x squared exponential 3x. The same thing here. So this and this cancels out. We have 2y on 3x. So this and this also cancel out. The whole thing is left with y squared exponential 3xy. So even though it looks complicated, this was the end result. Yes, it is. And then for our m with respect to x, we had the first thing we did, that one was quite easy. Y squared exponential 3xy. Y squared exponential 3xy. And then we merge them. The same thing. So our solution becomes y squared exponential 3xy equals k. That was all. So this becomes solution to the differential equation. Even though the process looks much complicated, but then the final answer is very simplified. Let's see if they give us any boundary condition, initial condition. So initial condition was y of 0 is equal to 1. So let's put that in C. Y of 0 is equal to 1. So when x is 0, y is 1. So you put that there. Y is 1, so 1 squared. Exponential 3 times 0 times 1 equals k. So this gives us 1 multiplying exponential 0 plus k. So our k is 1. So our actual differential equation becomes y squared exponential 3xy equals 1. When we want to make y the subject, you can actually make y the subject. You apply length to both sides. I think that one will also be complicated a little, but let's try. So ln y squared plus 3xy ln e equals ln 1. So ln 1 is 0, right? Ln 1 is 0. Ln e will also give us 1. So you have ln y squared plus 3xy is equal to 0. We can still make y the subject. So we can leave our answer as this one. So that's all for the first order differential equation. So you can try these questions. So 2xy squared plus 4 equals 3 minus x squared y prime. The second equation, y squared minus x dx plus negative 2y dy equals 0. And our third one is supposed to be xy prime equals y bracket ln x minus ln y. The boundary condition for this problem is y of 1 is equal to 4. So we can try these questions, and after you send it to us, and we'll review it for you. So thank you for your time.